Assalamu alaikum, dear students. We're back with another video lesson. In today's video lesson, we're going to talk about harmonics. We'll also go through the definition of a harmonic, the detail of harmonic, and all that. And I can tell you that harmonics are not something totally new because you've already learned something about harmonic in chapter 3, section 4, but back then we call that standing waves. We said, when do we get standing waves? If you have two waves, for example, if you have a string that is, let's say if we have, let's start with this one. If you have two waves of the same frequency, wavelength, and amplitude, but if these two waves are going, for example, in opposite direction in the same medium, then we get standing wave, all right? But remember, these two waves must have the same frequency, wavelength, and amplitude. Then we get something like this, right? And then we call this one, let's just write something nicer, and we call this one a standing wave here. So standing wave, it is a wave pattern that that occurs when two waves of the same frequency, wavelength, and amplitude move in the same medium but in opposite direction. Obviously, their speed must be the same too. Right? So, of course, if it's the same wave, obviously their speed is the same. Otherwise, it's not a condition. But if all the other conditions are the same, obviously the speed will be the same as well. So now that is what we're going to study with here. So what is harmonic here? Now, consider we have a string that both ends are attached or connected or fixed together here. So we're going to have a waveform that it looks like this one here. So this is, Gutman, previously, there's a standing wave. When you have the two ends of the string are going to be nodes here because these are restricted. They're not allowed to vibrate here, but here, in between the two nodes here, the center of the wave here, where it is a point where there is maximum freedom, maximum displacement, and we call this point an antinode or just antinode in here. So we said that what happens if you plug this string much harder, let's say harder than this, then we get another waveform, and this is how it looks like. What happens if you plug even harder than this, then we get something that looks like this here. But these are, of course, it has to be the same, right? So let's just see if we can make it look a bit better, right? Something like this, right? So these are called standing wave here. Now these are, we're going to call these harmonics in here. But before that, this string is vibrating with a certain frequency, right? Let's just call it F1 or frequency there. Now, if the length of this string, let's just call the length of this string just L, okay? How much of a wavelength is this in here? So if you don't know this, you can always rely on drawing one full wavelength and compare the length of this wave here compared to this one just to see how much it is. Now you can see that I can tell by far here, you can even draw this one if you want to. The blue one is one full wavelength, the black one is one full wavelength. This is how much I have. So can I say that is half a wavelength? Yes. So according to this, or based on this, I can say that the length of a string is equal to half of a wavelength. Now if you want to cross multiply, then wavelength decata 2 times the length of a string here. Right? That is for the first wave that we have. But if we want to find the frequency, we know that, right? Speed of a wave, it is equal to frequency times the wavelength here. If I want to make the frequency the subject, it is equal to speed of a wave. By the way, this speed of a wave, it is going to be the speed of the wave on the string here, on the string, right? Divided by what? Divided by the wavelength. But we just said that speed of a wavelength divided by the wavelength. We just said that the wavelength that is equal to 2 times the length of a string here. So this is would be the frequency of the first wave that we have. Now, if you look at the second wave here, I can tell you that we can call this one second wave, right? So the frequency of the second wave, can I say it is twice the frequency than this one? Yes. How can I tell? If this one is one loop, all right, one circle, whatever you call that one here, I have, or there is 2 loops right in here. So I can say whatever the frequency of this one, the frequency of the second one is going to be 2 times the frequency of the first one. What about the third one there? Also, the frequency of the third one, we can say 3 times the frequency of the first one. And of course, we can prove that using that equation over there. Now, what about regarding the length and all that here? So if this is the same length here, how much of a wave is this? If you compare that to the wavelength that we have, obviously you will notice that. Right now, regarding the wavelength of this one here, we can see that starting from this point all the way to this, that is one full wavelength. So the length of a string will be the same as the wavelength for this one right here. What about this one? What about this one here? We can say this is obviously the same length as the previous one here. But if you look at this one here, this is one full, or starting from this one, doesn't matter. That is up to this point, that is one full wavelength, and this is half. So we can see, or we can say that the length, it is equal to what? It is equal to 3/2 of a wavelength. In other words, you can say length takata 1.5 of a wavelength here. And if you want to make the wavelength the subject, it is equal to 2/3 of the length. That'd be the wavelength in here. So you can see that 2/3, this is 3 section. One, we can see that 1, 2, and this is 3 sections. So 2 out of 3, right? Out of 3 section, that is equal to 1 full. 2 out of 3 section of the length, that is equal to 1 full wavelength. That is what we have. But there's one thing I need you to see here. As we go further down more and more, you can see that the frequency increases, right? Because whatever the frequency here is going to be 2 times as much. Obviously, the frequency and wavelength are inversely proportional. Frequency here is equal to 3 times as much, right? But what do you think will happen to both frequency and wavelength? Of course, these are inversely proportional, right? So as the frequency increases, the wavelength decreases. Let's redraw this one real quick. That is the first. This is the second, right? Let's use different colors. And then these are more. We can even draw more and more, by the way. Okay. So no matter how many you draw, as you go further down here, the frequency increases more and more, but at the same time, the wavelength decreases. Don't forget, these are, the ends are node in here, and then this one would be an antinode here. So the first wavelength that I have, it is, we have 2 nodes and 1 antinode. What about the next one here? And don't forget, in chapter 3, we've studied those, right? So these are antinode and antinode. These are nodes and nodes and nodes. So we said the first one, right? The length, it is equal to what? Or the wavelength here, it is equal to 2 times the length. What about the next one here? The wavelength, it is equal to the length. The third one here, the wavelength, it is equal to 2/3 of the length here. What about the fourth one here? It is equal to how much of this one? You can see that it is equal to 1/2 of the length of this one. As you can see, the wavelength was 2 times the length here, then it was the length, then it is decreasing more and more. But at the same time, the frequency, it is going to increase more and more. So frequency, or the first frequency, that is equal to V divided by 2L, which we set at. Now the next frequency that I have, as you can tell here, that'll be the second frequency. It is equal to what? We can see that it is equal to 2 times, we said the fundamental, right? That is V over 2L over there, if you want to say, right? So because if the wavelength is 2 times less, the frequency will be 2 times more. That is very obvious, you can see. If not, you could just, for example, write the equation there, right? Here, for example, it is equal to what? It is equal to V over just L, right? So whatever it is going to be 2 times bigger than this one, because this is divided by 2. So now, based on this, we can just like make a general equation for this one here, because the third frequency here, it is equal to 3 times V over 2L. Instead of doing all this now, we can write one equation for the frequency. We can say frequency equal to N times, Basha, or frequency of N. What are these, or what is this N? I'll tell you in a second. It is equal to V. That'll be speed again of sound, speed of the wave on the string. That is not the speed of a sound, divided by 2 times the length in there. Okay, so now these N's here, right? Now we're going to give these frequencies numbers here. We can call this one, for example, F1, F2, F3, and F4, and so forth here. So what are these N numbers here? These N, it stands for the number of harmonics. So what are harmonic exactly? So N could be 1, 2, 3, 4, and 5. N here would stand for an integral multiple of the fundamental. So bakurdaki babalan tanzare fundamental, right? So for example, now regarding the first, the fundamental, that is going to be 1 times this frequency. What about the second harmonic, for example, right? The second harmonic, yani F2, it becomes 2 times fundamental. See how many times fundamental? That is called the number of harmonic here. What about F3, for example? That is said F2. What about F3? It is equal to 3 times fundamental here. So this number 2 and 3 and all that, these are called number of harmonic, which is an integral multiple of the fundamental. Tanzare fundamental, for example, 2 times 1, yeah? 3 times, 5 times, 10 times. These Zanzara, that is called the integral multiple of the fundamental, which we call them harmonic. Now there's something else which is called harmonic series, Baba. Harmonic series, it includes the fundamental plus the integral multiple. Yani, we have harmonic series now, if you want to call them harmonic. What is harmonic series? Yani, it's like a series of all these harmonic here. So you can say harmonic series, that would be the fundamental frequency, Basha, which is this, and, or you can say plus, an integral multiple of the fundamental, and it's Zanzare fundamental, like that would be 2 times fundamental, for example, 3 times fundamental, right? 4 times fundamental. These are called harmonic series, Basha, right? Or could be 5 times fundamental one, yeah? So this is what harmonic series it is equal to. So like it is a series, it is a chain of frequencies that we have, right? Include the fundamental, so whatever the fundamental is, and plus an integral multiple, Zanzare fundamental, like 2 times, 3 times, 4 times, 5 times, and so forth. These are basically what we have in harmonics. So the first thing that we have, it is a string. Don't forget, of course, there always a question says, like, what is the longest wavelength, Basha? What is the minimum frequency? And what is the fundamental frequency? So don't forget this. Now, let me redraw this one and tell you the summary of what I just said, for example. So this is the fundamental frequency that we have. With my fundamental frequency, it is the minimum frequency that a string is vibrating with. So that would be fundamental frequency. Minimum frequency that the string, we can say, vibrates with. Here, of course, we have a string, right? So that the string is vibrating with. Vibrating with. All right. Now, regarding this, we said we have to find any frequency, or to find the frequency of any harmonic, you can only use this equation. Frequency of any harmonic, all right? It is equal to the number of harmonic times the speed of a wave on the string divided by 2 times the length. Gutman and Akash. It is equal to 1, 2, 3, 4, and so forth. So we have both odd and even numbers here, because later we have number of harmonics that are only even number later. That is for the frequency. Do we have any equation that we can use to find the wavelength of any harmonic? The answer is yes. So for the wavelength here, we can say wavelength of any harmonic, right? Right, it is equal to what? It is equal to 2 times the length of the string here divided by the number of harmonic. If you remember in chapter 3, we were saying 2 times the length divided by the number of antinodes, right? But at this point here, we're not going to write it antinode, even though it is the same thing here, but it is just easier to say the number of harmonic. Let me give you an example. All right, so for example, let's say that we have a standing wave, all right, or the fundamental frequency on a wave, the fundamental frequency on a wave that is equal to, let's say it is equal to 100 hertz. Okay, that is the fundamental frequency on a wave. What is the third harmonic? All right, so according to this question here, because we don't have the length and all that, so we could just write what we've learned before. That non-frequency of any harmonic, it is n equal to times this much in here. And this is the same as the frequency of a fundamental there. Good man. So if you have the fundamental here, so to find the second harmonic, you could just say 2 times first. If you want to find the third harmonic, you can say 3 times the fundamental, and so forth in here. So if you have the fundamental, what is the frequency of the third harmonic? Third harmonic, yani 3 times fundamental, and that would be this one here. But we can also have, for example, if we have the length of a string, okay, so third harmonic, it is going to be this much, by the way. And how do we know how many harmonics are there? If the diagram is given, you can always count the number of loops. If not, you can count the number of antinodes that you've done in chapter 3 here, because that would be the same thing. But for now, counting the number of each loop, that would be 1 harmonic, so that is going to be the third harmonic. One more question. If the length of this string is, let's just consider the length is 5 let's just say 15 centimeter, Masha. If it is centimeter, what is the wavelength of the third harmonic? Now, for the wavelength of third harmonic, all you have to do is just multiply 2 times the length divided by what? Divided by the number of harmonic, third harmonic. So it is going to be 2 times, all right, 15, because that is the equation. 2 times the length. The length is 15 centimeter. We'll convert that to meter in a second, divided by 3. So that is going to be 30, right? we can say centimeter divided by 3, that is going to be what? That is going to be 10 centimeter, or you could just say 0.1 meter. You could have converted this to meter at the beginning. If not this one, that would also be fine as well. So this is the wavelength as well. And of course, later we have questions that it says, they will give you questions. For example, if the third harmonic, let's say if the third harmonic, it is 120 hertz, Asha. Now, what is the second harmonic, all right? Now, what do you do if you have a question like this? That is also very easy, but you can write a note for yourself. Whenever you're given the frequency of any harmonic, always find the first or the fundamental frequency. Because once you have the fundamental, if you want to find any frequency, you'll just say this multiplied by that. Like we said earlier, for example, if you have the fundamental, you want to find the second one, you'll just say 2 times fundamental. You want to find the 9th harmonic, you'll just say 9 times fundamental. So your fundamental is the key. Always find fundamental frequency first if you don't have, right? So now we have the third harmonic. We want to find the second harmonic there, right? So, but we know that, right? Third harmonic, it is equal to what? It is equal to 3 times fundamental, right? So if the third harmonic is 120, it is equal to 3 times fundamental. Now both sides divide by 3, right? So this is going to be 40. So we can say fundamental frequency, it is equal to 40. Now, once you find this one, you can find any frequency that you want to find. So now if I want to find the second, we'll just say 2 times fundamental, and that'll be it. So 2 times 40, that is going to be 80 hertz. And of course, that's been an Wazari. So this is the second harmonic. This is how easy you can do that there. All right. What if the question says, for example, find, maybe they'll give you the frequency. They'll ask you to find the length of the pipe in here. So now, for example, if the second harmonic is 80 hertz, what is the speed of the sound then? Let's convert that to this question here. If the frequency of the second harmonic, it is 80 hertz, Basha, and then the speed of the wave on the string, it is 240 meter per second. Basha, can you find the length of a string? Absolutely yes. Because we're given second harmonic, so just write this. What is the equation for second harmonic? Because the question is asking for length, so you have to write the equation with the length in here. So we have this equation, the fundamental frequency, the cat n times v over 2l, right? So if it is the second, we'll just say second. It is equal to, at this point here, n would be 2 because it is the second, v divided by 2l. So now the second harmonic, it is 80, right? Now, something before that, if I want to find the length, can I just swap this to, yes, so we can say the length, it is equal to, you can cancel out this 2 obviously here. So v divided by second harmonic, that is 240 divided by 80. So you could just find the math or do the math and you can find that. So that this 2 cancel out. So 24 divided by 8, that is going to be what? That is going to be 3. So we can say 3 meter in this case. These are random numbers, but this is how you can find whatever that is unknown there. Okay, and of course there are a lot of questions, but if the question is ever saying, what is the wavelength of the longest wavelength, or what is the wavelength of the fundamental bubbling of the string at the fundamental frequency, Awkati, these are keywords that you have to find the wavelength for the longest wave. Longest wave, Baba, that is the fundamental frequency. Okay, so these are what we have. Gutman, of course, once you plug a string, it vibrates. Gutman, later length, dakata, or the wavelength, dakata, 2 times the length. These are both side node, and this is an antinode, so you can call this one fundamental, which is the minimum frequency that a string is vibrating with. Kata, what is fundamental? It is the lowest frequency of a vibrating, let's say a vibration on a standing wave. That is what is called fundamental. Gutman, if a string vibrates with 2 nodes and antinode, these are keywords, then the wavelength produced it is equal to maximum wavelength. Length 1 over 2 wavelength 2 times the length. But the speed of sound that is equal to this much, so frequency on this, we can replace the wavelength of the fundamental with 2L, so this becomes an equation now. And of course, we have this Wazari question that says the wavelength of the fundamental frequency, the fundamental frequency, that is the longest wavelength on a vibrating string. The longest wavelength All right, on a vibrating string, you can use this equation here. It is equal to 2 times the length divided by n. If it is fundamental, yani the n is 1, so this would be 1, 2, that is, in this case, is going to be 2 times the length, and that would be the wavelength. I got it. All right, we have few key terms here. قلت معنى harmonic series. What are harmonic series? قال لي قلت معنى it is a series of frequencies. It is a bunch of frequencies that include the fundamental frequency, that is F1, all right, and also an integral multiple of the fundamental. What do you mean by an integral multiple? That means n times fundamental. When you on this n, that would be the integral. It could be 1, 2, 3, 4, 5. That is what it is. So harmonic series that include the fundamental and an integral multiple of the fundamental. Sanzare fundamentally. What about harmonic, Baba? It is an integral multiple of the fundamental. That would be this. So harmonic, when we say, for example, the fifth harmonic, that would be 5 times the fundamental. This 5 times, that would be the number of harmonic here, which is, we can say, an integral multiple. Fundamentally. And then we talked about this one here. If you have a string that vibrates with, for example, with 1 antinode and 2 nodes in here, so that would be the fundamental frequency. That is the minimum frequency or the simplest type of vibration we can have. Masha? All right, but manir, if you want to find the wavelength here, the kata 2 times the length divided by n, which is equal to 2 times the length there. Now, if you look at this one here, we have 2 loops. If you want to count the number of nodes and antinodes, here we have 1 antinode and 2 nodes. So obviously, the number of nodes on a string, it is always 1 more than the number of antinode. You can see. All right. What about here? All right. So we have 2 antinodes. Kata, I must have 3 nodes in here, as you can see over there. So the length of the string the length of the string would be the same as the wavelength here, but this frequency, because we have 2 loops, you can say it is twice as the fundamental here. What about this one? 3 loop, that would be 3 times as much, 4 loops, 4 times as much, and this is how you can tell. But based on this too, here how you can find the wavelength too, we can now of course have a general equation for the frequency, that on f of any harmonic, n would be harmonic, n times v over 2l, while n equal to these numbers. And if you want to find the wavelength, the kata 2 times length divided by the number of harmonic. All right, question 22 says, what is the fundamental frequency? Fundamental frequency is the minimum frequency that a string is vibrating with, right? Now the second part of the question says, how are harmonic related to the fundamental? Harmonics are integral multiple of fundamental. Harmonics are Tanzare multiple, and that would be the harmonic series, right? This is how they are related. It's fundamental, lowest frequency of a vibration on a standing wave, while harmonic is an integral multiple of the fundamental Tanzare fundamentally. We have this also, this Wazari question says, which or one of the following, it is correct, all right, to find the harmonic series of a standing wave on a vibrating string, because here we have a vibrating string. Later on, of course, we can have a pipe that is open at both ends, and could be a pipe that open at one end, closed at one end also too. So which one of these would be correct? That is, of course, is going to be A, because fundamental n times v over 2l, that is the correct answer. Now, the next question that we have says, which of the harmonic series of a standing wave on a is the harmonic series of a standing wave on a string? Once again, that means for harmonic series on a standing wave, it is all the integral multiples. We have, in other words, we have both even and odd numbers here. So which one of these are both even and odd number? That is going to be option A. What about option B here? These are only odd harmonics, which is later is going to be for a pipe that is closed at one end. Later, we have only the even numbers, so this is incorrect here. We have even and odd numbers, but it doesn't start or begin from 1, so we don't use this one right there. Okay, so now we're left with the only correct answer, and that is option A. All right, now we have a question here, says what? If, or the figures below show a stretched vibrating string, and it is several of its mode. The length of the string is 2 meters. Watch out for this one. The next thing says, what is the wavelength of the wave on the string in A, B, C, and D as well? So you can see here, this is 1 loop. So can I say it is the first harmonic? Yes. 2 loops, second harmonic, third harmonic. fourth harmonic, we can say. So the question says, what is the wavelength? To find the wavelength, we have this general rule, that 2 times the length divided by number of harmonics. So if I want to find the wavelength of the first harmonic, right, lambda 1, that is going to be, it is equal to 2 times the length gets in that, it is 2 meter, divided by what? Divided by the number of harmonic. The first one is just 1, so that is going to be 4 meter. What about the wavelength of a second one? Right, we'll do the same thing, 2 times the length, which is 2, divided by 2, these 2 cancel out, that is going to be 2 meter. What about the wavelength of the third one? 2 times 2, right, divided by 3, that is 4 over 3, which is 1.331, yeah? Okay, that is going to be in meter. What about the fourth one here? That is 2 times 2, that would be the length of a string divided by the number of harmonic, which is 4, that is 4 over 4, which is equal to 1 meter. This is how easy you can do these questions, and we had similar questions in chapter 3 as well. Now this is a question we can say it's a bit different. Now this is something that is 4 harmonics, we can say. It says, what are the first 3 harmonics of a note produced on a 31 centimeter long violin string if waves on this string have a speed of 274.4? Once again, these are pretty easy. But remember, it says, what are the first 3 harmonics? So that is going to be F1, F2, F3 here. The reason why they say first 3, it is so that you can start from 1. All right, if they were just saying what are 3 harmonics, you could have just found any 3, that would be fine. The length, this is the length, but don't forget, convert this one to meter, that is going to be 0.31 meter. And then we have the speed of the speed on the string as well, which is this much. So let's find 3 harmonics. Good man, F1 nakata, n times. So let's start with this one, Fn nakata of frequency of any harmonic, n times v over 2l. Right. So now, if we want to find the first or fundamental nakata, 1 times, even if we don't write this one, that is totally fine. 1 times v 274.4 divided by 2 times the length, which is 0.31. So that is going to be, it is equal to 443, that is going to be hertz, and that's how easy it is. Basha, what about the second harmonic? Do I have to do all this calculation again? No, just say 2 times the fundamental, which is 2 times 443, right? So it is going to be 886 hertz. These are all in hertz. What about the third harmonic? Again, 3 times fundamental, 3 times 443, and then just find the answer in hertz, and that'll be it. See, very easy concept. And of course, we have few Zadi questions here, but I would love to, the first one is easy, just copy paste of this one. I would rather to do the third one here. And let's do this together. It says, a standing wave is produced on a vibrating string fixed at both ends. So we have a string, don't forget, and you can underline this because later we have a pipe that is open. Of course, we could have a pipe as well. Then things might change if it is closed at one end. If the frequency of the third harmonic, see, it is this much. Third harmonic, so F3 is this much. And speed of the wave is this much on the string. What is the wavelength of the longest wavelength? I need you to underline this word here. When it says the longest wavelength, that is the wavelength of the fundamental frequency, while they gave us the third harmonic. So what am I supposed to do at this point here? Because I have the third harmonic, frequency of the third harmonic, and I have the speed, I can use this to find the length of the string, right? Okay, so if I find the length of a string, because you do know that, if you want to find the length of the longest wavelength, so the question says, what is the wavelength of the wavelength of the longest wavelength? Longest wavelength, yani L1, which is equal to 2 times the length divided by 1 if it is the longest, right? But I need to find the length of a string. Do I have that? The answer is no. So how can I do that? Well, one method you can do that is by doing this. So here's the thing, all right? We can say third harmonic, it is equal to 3 times V over 2L. Do you agree? Absolutely yes, all right? So now all I have to do is just find the length here. So how do you find the length? It is equal to 3 times V divided by what? Divided 2 times the third harmonic, all right? So once again, 3 times, the speed is 345 divided by 2 times the third harmonic, which is 575. Okay, now let's find the length of the string now. So that is going to be 3 times 345 divided by 2 times 575, and that is going to be 0.9. So the length of the string, it is going to be 0.9 meter. Now all you have to do, just, we'll say 2 times 0.9, right, divided by 1, which is going to be 1.8 meter. That is how easy it is. Where's 1.8 meter? That is the answer to this, 1.8 meter. That is one method, all right? There is also another method you could do. I mean, actually, no, all right? That is how easily you could do this one. By the way, you can do this method here. You cannot just use V, it is equal to frequency times the wavelength. You cannot do this one, because if you find this wavelength, that is going to be the wavelength of this third harmonic that we have is not the longest harmonic there. But there's also this one, you could do that. For example, if you find this one, that is the the wavelength of the third harmonic, all right? So you could just multiply by this much. You could do that by 3, because third harmonic is going to be 3 times less than that. You can also do that to find it. Now, there's another thing here, all right? Standing wave in an air column. So we're done with the string now. We have another case. Can we have, or like, do we have standing wave in a pipe that is open at both ends? Yes, that is called air column here. So we have a pipe. Okay, we have a pipe, and we call this one air column. So let's rotate this. Now, of course, this is a pipe that is open at both ends, yeah? So what exactly do we have? We're going to have a standing wave right here. So, but how do we do that here? Now, regarding this one, change color. So once we have an open pipe here, so it is going to, right, once, for example, air is blowing in one of the pipe, you can see that part of the air is going to be reflected, and then this reflection produces another wave that will be produced in opposite direction here. Then we get a standing wave right here. So this is, we can say, the first standing wave that we can ever have. And I will believe it will be easier. Let's just get rid of this one and just draw something like this. It might be a little bit easier to notice the difference between this and a string that we just studied here. So if this is a pipe that is open, as you can see at both ends, so we're going to have a standing wave here. This standing wave, this is how it looks like. What is different between this and the string that we've studied here, right? If you remember, for string with on both sides are nodes in here. And the center, of course, was an antinode, right? Now, what we have, it is exactly opposite at this point. So we can say the two ends are antinodes, right? And the center is a node here. I can tell you that it's almost the only difference between a pipe that is open at both ends and a string right there. Okay, why do I feel like this thing is still not up to the expectation of, or the way that is supposed to look like? So here's a pipe, right? That is what it should look like. So these are both ends, it is an antinode, right? So where particles have, or air particles at this point have maximum freedom to vibrate, while on the string they were restricted. But here, the center is a node where that is the point where the particles are restricted here. So at this point, watch this. If we have, or the length of this pipe is just L, how much of a wave is this? Once again, if you're not sure how much of a wave is this, you could just draw one full wavelength. And then you could draw the other side too if you want to here. Now, how much of a wave is this? You could start from, for example, somewhere that looks like at this point here, and then up to this point. How much of a wave is there? That is from, we can see this part to this part. Isn't that half a wavelength? Yes. So we can see that the length here, it is equal to half a wavelength. And if you want to find the wavelength, it is equal to 2 times the length. That is the minimum vibration that we can ever have. And you can call this one F1 or fundamental frequency for a pipe that is open at both ends here. Again, baby. Basha. So this is a pipe. We can say a pipe that is open at both ends. Basha. Pipe open at both ends. Because later we have a pipe that is closed at one end. You can say that. So this is the minimum frequency that we can have. Of course, it's going to be the same thing as before. So what happens if, for example, the vibration increases there? Then this is what we get as a result, right? So now this is an antinode, another antinode. Let's make this one nicer. This is another antinode here. So you can see the number of antinode this time, it is more than the number of nodes. So one more. So this is going to be, and how do we know what harmonic is this? Previously, Gutman, you can measure the number of loops for a string. We could have measured the number of antinode, but later, in order to know the number of harmonic, you'll have to count the number of nodes. So first node or one node, that is going to be first harmonic, two nodes, second harmonic, three nodes and three harmonics, and so forth and forth. All right, so let's draw one more. It's the same thing here. So it's going to be something like this. All right. So now this is another standing wave here. The ends are going to be antinode. These are antinode points, right? And then these are nodes right here. Okay. So you can see number of antinodes are always one more than the number of nodes, which is exactly opposite to the string here. So whatever the frequency that we have, it is fundamental. The frequency here for the second one is going to be 2 times the fundamental. What about the frequency of this one here? 3, that is going to be 3 times the fundamental. So in this case, there's no difference. In terms of equation, there is no difference between the equation we've studied for the string and the equation for a pipe that is open at both, and don't forget. So now, based on this, we can generalize an equation. Frequency of any harmonic, it is equal to n times v divided by 2 times the length. Again, maybe n akashdakata 1, 2, 3, 4, and so forth. So we have both even and odd numbers here. For the wavelength, right? For the wavelength, it is equal to wavelength of any harmonic. It is equal to what? It is equal to 2 times the length of a pipe divided by the number of harmonic, which is, again, it is equal to this much. But I can tell you that if we consider this another difference, here, this v, that would be speed of sound, right? Speed of sound, or let's say speed of sound of air, right? Inside the pipe. Previously, we were saying this speed for the string, it was the speed of a wave on the string, but now it is going to be speed of sound inside the pipe, or speed of sound in air. We can say that since these are air pipes, musical instruments that work with air here. So this is everything that you need to know. Basha? Now, if I, once again, this is pretty much everything regarding the wavelength, or regarding how to, this is the longest wavelength, Basha. This is, by the way, with Malira, the length of the pipe, it is equal to 1 wavelength. If you start from this point all the way to this point, that is 1 full wavelength. There is one more thing that has never been in Uzari, Baba, and that is these diagrams. If they brought these diagrams in Uzari, how do I know which harmonic it is? And how do I know whether this is the one that I need to look for? But man, if it is a pipe that is open at both ends, they become an antinode. So whenever you see antinodes at both ends, this is a pipe, right? This is a pipe that is open, right? Open at both ends, because later you'll see a difference here at both ends there. So particles have maximum freedom to move here at the ends, but at the nodes, they are restricted there. So if you, for example, we said if you want to know how many harmonics, just the number, count the number of notes. So 1 note, first harmonic here. What harmonic is this? 1 note, 2 note, 3 notes in here. So this is the third harmonic. It could be any other diagram. This is how you can tell. And this is regarding the equation. And these are 2 musical instruments that are considered as a pipe that is open at both ends. We can say saxophone and, of course, a flute as well. To find the wavelength of any harmonic, Gutman used the same equation that we said it. So in terms of equation, there's nothing different between this and that of a string here. Okay, increasing, there's one thing you need to be aware of that. Previously, we were saying in chapter 3 that increasing the temperature will increase the speed of sound in air, which increases the frequency of a sound. That is, we can say, the only thing that affects the or change the frequency beside changing the frequency of a source. And why is that? Because based on this equation, if temperature increased, watch this, if temperature increased, of course, the particles, right, going to vibrate faster. Or if temperature increased, the kinetic energy of the particles increase, right? If kinetic energy increases, that means the particles are going to vibrate faster. If there is a faster vibration, that means the speed of the particle is going to increase, right? Or speed of sound is going to increase. If speed of sound increases, and that is directly proportional to the frequency, that of course makes the frequency to increase as well. So which doesn't matter which frequency it is, but most of the time they'll ask you if, for example, increase the temperature, that affects the fundamental and the frequency, Babylon. Is that or does that increasing temperature, makes the frequency to be slightly higher or slightly lower? Because these two are directly proportional. And of course, this is proportional with this. So increasing the temperature increases this. Increasing this would increase the frequency. Kata, it makes it slightly increase. And that is the next question. It says, the fundamental frequency of any note produced by a flute will vary slightly with temperature, change in the air. For any note, for any frequency, for any given note, will an increase in temperature, so if the temperature increased, Basha, produce a slightly higher frequency, fundamental frequency, or a slightly lower fundamental frequency. But not if we increase the temperature, that increases the speed, which increases the fundamental at this point. So increasing the temperature will increase the speed of sound in air, which increases the fundamental frequency F1 of a sound, because these two are directly proportional. But again, if these two are increased, for example, if these two are changing here, of course, the lambda or the wavelength must be considered constant. Hamuzare, when you compare two things, no matter how many other variables you have, you must keep the other variables the same. Agarna equation, of course, does not work. Not it does not work. We might not know which one is affecting the one that we're looking for or trying to measure. All right, so take a look. These was added question. Here says, in a pipe that is open at both ends, right? If both ends are open, only even harmonics are present. No, good mind. It's the same as a string. Only odd harmonics are present. No, right? Both even and odd harmonics are present. Yes. No harmonics are present. That is incorrect, which is option C here. One of the following is correct to find the harmonic series of a standing wave in a pipe that is open at both ends. It is the same as the first string, so it is going to be n times v divided by 2l. All right, we also have another question here. It says a pipe that is open at both ends. Always underline this because depending on whether given, of course, the equation might change. Both ends has open at both ends has a fundamental frequency. So this is fundamental. When the speed of sound in air is this much, says what is the length of this pipe in here? So easy, right? Good man. Frequency of any harmonic that n times v divided by 2l. If you want to find the length of the pipe, just swap it with the fundamental here. So length decata n times v divided by 2 times f and whatever n is. All right. So fn here. So which says fundamental frequency. So fundamental, that is 1 times speed decata, it is 331 divided by 2 times fundamental, which is 320. Now all you have to do, just do the math and you can find the length, which is 0.52 meter. That would be the length of the string. That is the first requirement. The second says, what are the next two harmonic? Ebasha, if we have the fundamental already, what do you think are the next two harmonic? All right, so the next one is going to be F2. F2 decata 2 times F1. Do you agree? What about F3? Decata 3 times F1. So just do the math and find the answer. And that'll be it, which is 640 and 960 hertz. All right. There's this question too. These questions, you can see that these are very similar to one another. We can see that it says an open organ pipe, it is 2.46 meter long. That is the length. The speed of sound is that much. What is the fundamental frequency? Yalla baba, fundamental frequency decata. Because it says fundamental, kata 1 times v divided by 2l. Even if you don't write 1, it's okay. So 345, that is the speed, right, of sound, divided by 2 times 2.46. So the fundamental now it is equal to 70.1 hertz. That is this. That is the first requirement. Second says, watch this, says how many harmonics are possible in the normal hearing range? That's also another interesting question here. Now we know that in the normal hearing range, we have 20 to 20,000 hertz, right? Now, let me give you an example. Let's say you're going to a store to buy something, maybe to buy a, I don't know, like could be a purse or whatever, a jacket or a bag, or could be whatever, right? Let's say you have 100,000 of Iraqi dinar, right? Let's say at this point, right? Inshallah, soon you will have millions. But here's the thing, for example, now, if the price of every bag is 20,000 dinar, how many bags can you afford or can you buy, right? So you will just say, right, the total money that you have in this case, which is 100,000 dinar, divided by the price of each bag, right, which is in this case, let's say 20. All right, can we do the same thing or use the same analogy to find how many harmonics do we have in the hearing range? Yes. What is the maximum frequency of a hearing range? That is 20,000 hertz. And we can say that the frequency of every harmonic is 70.1. So can I simply divide 20,000 by 70.1? Yes, it is the same as if you have the total price divided by the price of every harmonic. Yeah, that would tell you how many harmonics are present there, because the question says how many harmonics are possible in the normal hearing range. All right, so simply we can say we can just simply say n1, yeah, because we can say, okay, simply we can say n, it is equal to what? N equal to the frequency that we have, Basha, divided by the fundamental frequency. All right, do you remember this equation here? On fundamental dakata, n times whatever the frequency that we have. F sub n, it is equal to n times fundamental. So now we have the fundamental, we have the frequency of, let's say the range of hearing, and then all you have to do is just find the number of harmonic. So this is 20,000, right? It is equal to n times, what is fundamental? 70.1, right? So all you have to do is just find the number of n, which is equal to 20,000 hertz divided by 70.1 hertz. And in this case, of course, what do you get? You get 285.2, right? But now, so far you've seen, for example, when we were using the number of harmonics, did we even have, for example, did we ever have any harmonic with a decimal number? No, harmonics always come in whole numbers. Starting from 1. We don't even have 0, by the way, all right? So starting from 1, 2, 3, and then, of course, it can go on and on and on. So we don't have like half a harmonic, let's say, or what is it called in here? So just divide 20,000 by this much, then you will get 285. This 0.2 we just take off because we want to know how many whole harmonics are there, and that would be this. And you might say, for example, what about the 20? If you divide 20 by 70 point this much, you get 0 point something. And of course, we don't consider that because all the harmonics that we have start from 1 and then so forth in here. So you can see that we've done it here, right? Starting from the first one here, 20 divided by 70.1. 70.1, you get this much. But even if you don't write this one, that is fine because you always use the biggest number, divide by what do you have, that'll be the number of harmonic that you can have in that hearing range. And of course you can see, since n must be an integer, so the maximum possible is 285. Therefore, the number of harmonics possible in the normal hearing range, that is going to be 1 to 285, or simply just 285. This is also a few questions here. It says if a pipe that is open at both ends, if F3 is this much, right, what is F2? We've solved a similar question like we've solved actually was this question here, right? So we said always find fundamental first. Get man F3 dakata, that is for this one here, dakata 3 times F1. Always find F1 here first. 3 times F1, with man both sides divide by 3, F1 دكاترة 40. Once you find F1, then of course finding any other harmonic would be very easy. So now F2 دكاترة 2 times F1, 2 times, what is the fundamental? 40. So 2 times 40, that is equal to 100 hertz, and that is going to be the second harmonic. So always find fundamental, then whichever that you need to find later, of course, is going to be easy. All right, now here's also another question. Says, a pipe that is open at both ends has a fundamental frequency of this much. So this is fundamental. And the speed of sound in air is this much. So this is, we can say, fundamental V1 F1, F1 V1. What is the fundamental frequency of this pipe? And it has the same length. So now the new fundamental, we can say that it is unknown if the speed of sound in air increases to this much right here. This question can be solved in two different methods. I'll try to solve them both for you. So, but first of all, because the length is not given here, if I use fundamental and speed, can I find the length of a pipe? Yes. So, for example, fundamental, دكاترة, n times, actually we don't have to write n because n is 1 for fundamental. That would be speed over 2L. So let's find L, دكاترة, V divided by 2 times fundamental. V, it is 331 divided by 2 times fundamental, which is 456. Yeah, find the length here, whatever the length is equal to. And then for the new fundamental, when the temperature change, right, دكاترة 1 times V. Now what is the new speed? It is 367 because the speed is changing. So of course, now the fundamental will change. So first, let's find the length here. We can say 331 divided by 2 times 456. The answer is going to be, or the length is 0.363, right? That is in meter. Now all you have to do is just multiply by the same length because the question says same pipe, 0.363. Okay, so let's do this one here. 367 divided by 2 times 0.363. The answer is going to be what? It's going to be 506, and that is B. So this is how you can do that. So the new fundamental, it is equal to 506 hertz. There's another method to solve this question, which is easier actually. What is the second method? So of course you can write it down if you want to. The second method is this. Now because fundamental, right, and speed are directly proportional, right? So I can say, right, fundamental 1, it is equal fundamental, well, let's say the new one because we're trying to find the new fundamental, right? So new fundamental, right, divided by the old fundamental, it is equal to, these are directly proportional. So we can say second speed of sound in air divided by the first speed of sound in air. If not, you can write F2, but be careful. This F2 doesn't mean the second fundamental. That would be the new one. So I would just rather keep writing the new one, but that is the second velocity over the first velocity. These two are same both. And previously we said that if they're inverse, of course they will go opposite to one another. But here, if it is direct, so they are just the same here. Man, if they were inverse, man, they would have been on the same line like this, right? But since these are direct, so these are totally fine. So you'll just write them side by side or whatever you call that one. So the new one is unknown, all right? The old one is, what is the fundamental? It is 456 is equal to V2, it is 367. V1, it is 331, right? So just divide this one and multiply by that. Let's see what is it equal to. It should be the same answer. So 367 divided by 331, right? And then multiplied by 456. Of course, the answer is the same thing. So we can say F1, our new fundamental, دكاترة 506 hertz. That is also true, which is easier, obviously. But I would, if you're not good at this, I would recommend using the longer way. It is safer. All right, the last thing that we have is if we have a pipe that is open and bubbling, if we have a pipe that is closed at one end, that would be the last thing that we can have regarding harmonics here. So what exactly is this? That is going to be the third case that we have. Now, if we have a pipe that is closed at one end, like this pipe in here, So, of course, once they are blown, there will be a standing wave or harmonics here. This is how it is going to look like. So this is the lowest frequency that we can have, and we can call this one fundamental. But before that, you can see that one end is closed, so this end becomes a knot in here. On this end, it is open, so air particles have total freedom to vibrate. That is an antinode in here. So we call this one F1, or the fundamental. If this is the length of a pipe, all right, let's just call it L. How much of a wave is this? We'll say the length of a pipe, it is equal to this. If you're not sure, draw one full wavelength and compare that, Basha. See how much of a wave is this. All right, so now you can draw the other part too if you want to. How much of a wave do you think I have? I only have up to this point, right? Isn't that how it looks like? How much of a wave is this? Isn't that a quarter of a wave? Because that would be half. This 3/4, and this is one full wavelength. Up to this point here, this is how much I have, right? And that is only a quarter of a wavelength. So later determining the length of a pipe, it is equal to a quarter of the wavelength here. So the wavelength, if you cross multiply, it is equal to 4 times the length of a pipe in here. So this is going to be the fundamental wavelength for a pipe that is closed at one end here. Basher, this is the fundamental. What is the next harmonic that I can have? So let's just zoom out this one here. All right, what is the next harmonic that I can have here? The next harmonic that I can have is this. So if this is the first, watch this. The next quarter of every quarter of a wave, you can say that'll be sort of like a harmonic here. But I need you to be careful with this word or this phrase because there is something tricky here. If we have the next harmonic, because that is a quarter of a wave, yeah? So that was the first, let's say. And then if this is another quarter of a wave, this part here becomes a node. Now, if we have a node, the particles have no vibration. If there's no vibration, will there be any sound here? The answer is no. So now this is supposed to be F2, but F2 is a node. If it is F, that was F1, okay? So that's supposed to be F2, but since it is a node, there's no sound here at this point. So we're just gonna continue here until we get, for example, to another antinode here. That'll be another sound that is here. That'll be the next sound that is here. But how much of a wave is this? Isn't that the place of a third harmonic here? Yes, and if you want to find the wavelength here, you can see that is 3/4 of a wavelength here. Don't forget, okay? So the length, the 3/4, the length of a string here, the pipe, it is 3/4 of a wavelength. It is equal to 4/3, we can say, of the length, then it is equal to one full wavelength. Basha, that is this thing right here. Now, what would be the next frequency what is the next harmonic here, Baba? So if I add one extra, let's say one extra wavelength here, I'll get another node here. So isn't that supposed to be F4? Because every quarter here, it is equal to a frequency here. But once again, there's another note, so there's no sound here. So we have to continue. The next one that you hear, it is going to be the 5th harmonic. So now, you're only going to hear sounds at F1, at F3, and F5 here. So have you noticed now, if we have a pipe that is closed at one end, we can only have the odd harmonic. What do we mean by this? That means we can have F1, right? We can have F3, we can have F5, and then of course the next ones are going to be F7, F9, and all that. So if we have a pipe that is closed at one end, and you can say if it is open at one end here, then we have only the odd harmonics. Basha. So the first fundamental, would be something. Third fundamental is going to be the same as, for example, previously, we'll just say 3 times F1, 5th fundamental, 5 times F1, 7th fundamental, 7 times F1. These are the same, but remember, we only have the odd harmonic. We don't have the even numbers right here. So how can we generalize this or write an equation for this one right here? So now, regarding the fundamental frequencies, we can say Fn بكاتا n times V لصار 4L. Why 4L? Because here we said previously, for the fundamental, the wavelength was equal to 4 times the length in here. So if it is F1, the cat of V, right, divided by 4 times the length one, yeah? So if it is F2, then it will say 2 times F1, which is 2 times V over 4L and all that, right? So instead of writing 2 and all that, we'll just call that an N. So now it becomes a general equation. So the equation for the antiharmonic equal to F fundamental, that is equal to what? N times V over 4L. And the number of harmonics would be 1, 3, 5, 7, 9, and it goes on and on, right? What about for the wavelength? If you want to find the wavelength for any harmonic, it is equal to 4 times the length divided by the number of harmonic. But again, number of harmonic, it is only the odd numbers. I got it. All right, but there is one thing I hope you notice, that when it comes to number of nodes and antinodes, it is way easier to tell compared to the other one, because here the number of nodes and antinodes are exactly the same. Basha, that is regarding this one. Basha, there is one more thing. If you're given a diagram, how do you know which harmonic it is based on a diagram that is given here? Right, that'll be the next thing here. Good man, this is the first harmonic that we have. 1 node and 1 antinode, right? What about the next harmonic that we have? It is going to, this is how it is going to look like. Let's just make this one look a bit nicer. Right? So here we can say 2 nodes and 2 antinodes, right? So these are nodes and nodes. What about the third? This is the third harmonic. This is the first. This is the third, right? What about the fifth harmonic? It is going to be sort of something like this. Diagrams are not perfect, but of course, niyat sharta. Okay, so that is number of node, number of node, number of node. So here you can see that I have 3 nodes and 3 antinodes right here. So 1, 2, and 3 here. Okay, so remember this. What if you've been asked, Basha, let's say there is a question tells you, if we have a pipe, Basha, or on this pipe that we have 7 nodes and 7 antinodes. How many harmonics, or what harmonic is this on the wave in here? If you have, or if you're given the diagram, or if the question has been asking about the number of nodes or antinodes regarding a pipe that is open at both ends, Basha, for any frequency or any fundamental that we have, you can use this equation to find which harmonic it is. We can say number of nodes plus number of antinodes minus 1. That would tell you the number of the harmonic that we have. So for example, we have a pipe, Basha. On this pipe that we have, let's say there are, so we have three nodes and 3 antinodes. What harmonic is produced on this pipe in here? By using this equation, we'll say number of nodes and antinode added, right? So that is going to be 3 plus 3, right? That is going to be 6 minus 1. It is going to be what? It is going to be 5. So this wave that is produced on this, let's say, pipe, it is going to be the 5th harmonic. Now we can reverse this question again. Let me just remind you this one more time. If the question says that we have a pipe, all right, on this pipe there are 3 nodes and 3 antinodes formed. Which harmonic is this? Don't say just 3, all right, because that would be misleading here. Gutman, on a pipe that is open, all right, and closed at one end, right? So we have equal number of nodes and antinodes there. So when you see 3 nodes and 3 antinodes, that doesn't mean third harmonic. No, you'll have to use this equation to find the number of harmonics over there, or which harmonic is there in here. So I've got my number of node plus antinode, and then minus 1, that would tell you the number of harmonics over there. Okay, that is going to be the 5th harmonic. Okay, so we could just say n in that case if you want to do that. Now we can reverse this question too. the question might say, if we have, like, for example, how many nodes and antinodes do we have for the 7th harmonic? All right, so let's do this one too. Or maybe starting with something easy, let's say, how many nodes and antinodes do we have for the 3rd harmonic? Pasha? Let's perhaps maybe draw a diagram. Okay. Good man, this is the 1st harmonic and this is the 3rd harmonic. How many nodes and antinodes do we have? That is 1 node, right? That's 2 node, right? So we have 2 nodes and 2 antinodes, right? Now, let's see if we use that equation, will we get the same answer without even needing to draw a diagram? You should, right? So, good man, which harmonic? The 3rd harmonic, right? So, good man, using this equation, we can say n it is equal to number of nodes plus number of antinode, right? Plus number of antinode minus 1. That should give you the number of what? The number of harmonic. So we said the 3rd harmonic. So this is 3. Do you agree, right? Okay, if that is the case, it is equal to number of nodes plus number of antinodes minus 1. Can I move this one to the other side? Yes, that would be 1 plus 3 and 3 plus 1. They got the number of nodes plus number of antinode. So now number of nodes and antinodes are going to be 4 nodes and antinodes, right? So 4 nodes and antinodes. So now if you count them 1, 2, 3, 4, that is going to be 4, yes? So easily by using this equation you can find out which harmonic it is, or if you know which harmonic it is, you can easily tell how many nodes and antinodes you have. That is number of nodes and antinode combined. What if the question says how many nodes do we have alone, right? So because these are equal, so in this case, whatever the number is, that's you just split them for both nodes and antinodes. You just divide by 2, yeah? Because number of nodes and antinodes are equal in this case, so just divide. So if it is 4, that is going to be 2 nodes and 2 antinodes, and this is how you can tell the difference between the two. All right, I think that is the most regarding this one. That is the most regarding this one. Let's I think it is time to go through some questions, but first let's go through these. What we have, man, this is a pipe that is open or closed at one end. Man, later, this is how it looks like. So the wavelength that is equal to 4 times the length, that is the fundamental wavelength, right? And then regarding the number of harmonic, we only have the odd harmonic. So 1st, 3rd, 5th, and so forth from there. Okay, this is what it is. Good man, the equation for frequency, it is n v over 4l, and n is equal to this much if you want to find the wavelength, the kata 4l divided by the number of harmonic, and these are what we have for every single let's say frequency fundamental. This is 2 times, let's say the next fundamental that we have, it is 3 times f1. All right, and these are more diagrams regarding this, but there's one thing I need you to be aware of that, and that is something that is called overtones here. What is overtone, Baba? Now we have the fundamental one, yeah. The other frequencies that come after fundamental, we call them overtone here. So this is the first fundamental frequency that we have. What is the frequency that comes after this? That is F3 one, yeah, which is right above this. So we call this one overtone. Over what? Over the fundamental, right? What about the one that comes after? That is going to be the 5th harmonic, right? Again, that is over this. But how do we separate this and that? You can call this one the first overtone and call this one the second overtone, right? The second one that is above or over this fundamental frequency. So now, of course, this table summarizes everything that we have said regarding a pipe that is a string, a pipe that is open at both ends, and of course, a pipe that is open at one end here. Now we have the 5th point here, which I believe we're going to explain this one in one more point, but let me just remind you here real quick. If you have a string, okay, that is a string. All right, so this is the first fundamental we can say, and this is going to be the second harmonic. This is how it looks like one, yeah. And if you have a pipe that is open at both ends, this is how it looks like. Right, these are nodes, these are antinodes, And these are nodes here. This is an antinode. If it is a pipe that is closed at one end, this is how it looks like. We have a node and an antinode here. And of course, we have other let's say, shapes as well. This is called the fundamental frequency, Basha. And then regarding for the frequency, what equation do we use? Fn, n times v over 2l. And then n, it is equal to 1, 2, 3, 4, and so forth. What about here? It is the same equation. The only difference we can say, this v is the speed of the wave on the string, here the speed of a wave in the air, which is divided by 2l, and a 1, 2, 3, and so forth here. What about there here? The equation will change. Fn dakata n times v over 4 times the length. See the difference? These are all of them are 2 length, but this is 4. And regarding the number of n, it is 1, 3, right? 3, 5, 7, and so forth in there. The fundamental frequency here, dakata, the longest half with the longest wavelength or fundamental wavelength here, dakata 2 times L, here 2 times L, but here it is equal to 4 times the length of the pipe in there. If you want to find the wavelength of any harmonic, Basha, you just divide this one by the number of n, and this one by n, but I got n, that is equal to the odd numbers only. And then there's more, right? Which is everything summarized in this case in here. Both ends are fixed, nodes are both ends are open, they have complete freedom of motion, but antinodes, we can say antinodes are both ends we have, but this is, if it is closed, one side is a node, the other side is an antinode. All harmonics are present, all of them are present, but here only the odd numbers. Fundamental wavelength, dakata on the 2L, 4L, equation of frequency equal to this, n over v, let's say, or nv times divided by 2L, nv divided by 4. Be aware of the number of harmonics there too. All right, and then for this point number 5, I'll explain this one later, all right, because we have a question related to this and a Wazari question as well. Point number 6 is the fundamental wavelength produced, it is half of the length of a pipe. You can see here, and also the fundamental wavelength, it is half of the length of a pipe. You can see here, which is not actually, let's just change this one here. But take a look, we can say the fundamental wavelength, that is, we can say 2 times, all right, or twice, that would be best, right? And for this one here, that is twice as well, because we said the fundamental wavelength, right, or the length, it is equal to half of the wavelength at fundamental, but the wavelength, dakata, 2 times the length if you want to here. So you could say the length, all right, would be half of the wavelength. If not, it would be best just to say the fundamental, dakata, 2 times the wavelength, which is exactly the same as it is written here. And then here, of course, we can see that the length or the wavelength, it is equal to 4 times the length of the string here. Okay, the next thing that we have, I got my number of nodes in a string, it is 1 more than the number of antinode, while antinode is 1 less than the node, if you can say. Later, number of nodes for a pipe that is open at both ends, it is more than the number of nodes here. So number of node would be, or the number of antinode would be node plus 1 at this point. Hopefully I didn't say it wrong here. But my data number of node is more. So whatever the antinode plus 1, that'll be the number of node. If you have, for example, the number of antinode, and if you want to find the number of node, you just add 1. If you have the number of node, you want to find antinode, just use the equation or minus 1, that'll be the same thing. This is also the same, this is actually opposite. On the number of antinode here, the kata node plus 1, because the number of antinode, it is 1 more times the number of the nodes here. But for a pipe that is closed at one end, these two are the same thing. And these are the diagram for each one of those right here. And this study tip, it is about what is written in the table, so there's nothing new. All right, let's answer these Wazari questions, and then we'll solve some questions next time here. It says, which of the following represents the harmonic series of a standing wave on a pipe that is closed closed at one end? If it is closed at one end, we only have the odd numbers, which is this one right here. What is the longest? Watch this. The longest wavelength, all right? That is for fundamental of a standing wave. A pipe closed at one end. بتمان the longest equation of any wave دكاتة 4 times the length divided by n. If it is fundamental, or longest would be fundamental, you could say 1, if not just for L. Which one is for L? That is going to be this one right here. At a time, let's say, at a time of producing a standing wave, in which one of the following causes the number of antinodes greater than the number of nodes here? I need you to be careful here. All right, it says in which one of the following cases the number of antinodes greater than the number of nodes? Basha bitman the stringy, the fundamental, or for the fundamental, the number of nodes is greater than antinode, right? Because there were 2 nodes, 1 antinode. Basha, what about for a pipe that is open at both ends? Man, these are both antinodes, antinode. There is a number of node in here. Got that? It is larger, right? What about for a pipe that is closed at one end? Man, the number of nodes and antinodes are equal here. Got that? Which one is greater? A pipe that is open at both ends. So vibrating string, pipe open at both ends, pipe closed at one end, or all of them. Now it is option B right here. All right, guess that'll be the end for this session. Inshallah, next time we're going to continue with solving some questions, and then so that you have all the idea regarding this one. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.